Thank you. We're on. How are we doing? How's everybody doing? Good. You can turn your mics on if you want. It's okay. Hi, Gabby. Hello, everybody. Okay, what we're going to do today is anti-derivatives. Let me if I yes. Anti-derivatives. And let me explain how it works. Anti-derivatives. Anti-derivatives. And sometimes this is called integration. Integration. Okay, both of these mean the same thing. Anti-differentiation or integration, fancy words for what we're going to be doing, okay? So I'm going to go to some line paper because maybe I can write better. There we go. Okay, so I'm going to erase this off. And let's say we had this problem here. I was thinking of a problem this morning. Oh, let's just make it simple. X squared. What is the derivative of that?
2x.
That would be 2x, huh? Right? Do you follow that? Do you agree?
Yeah, we agree.
Okay, well, anti-differentiation means that we have the derivative and we're trying to figure out what the original problem was. We have this derivative and we want to find x squared. So to do that, we use this symbol right here. This is your integration symbol, kind of like an S a little bit. In the book, you can kind of see it. This will be on page, let's see, if you have your textbook. Point 1. So you'll probably see the symbol on page 392. You see a symbol. It kind of looks like that, integration. And in here, we're going to put 2x, and behind it, we're going to put a dx to show that we took this is the derivative, okay? This is your derivative form. And so now we want to solve it. So how did we get this answer? We multiplied it 2 times the x, right? And then we subtracted 1, right? We multiplied by 2, and then we took 2, take away 1 is 1. So the antiderivative is just the opposite. Instead of multiplying, we're going to divide. And instead of dividing and instead of adding, instead of multiplying, we're going to divide, okay? And instead of subtracting, we're going to add. So the antiderivative of this is we're going to pull this 2 out of here. This 2 is going to stay. We can write it like this. And what we're going to do is we're going to increase the power of this x. Instead of making it smaller, this is x to the 1. Now it's going to be x to the 2. And we're going to put it over 2. So what we are going to do is we're going to increase the power of x. Instead of decreasing it like we did here, we're going to add 1 instead of subtracting 1. And then we're going to put, instead of multiplying by 2, we're going to divide by 2. Now, we originally had this 2 here, so we just project that down. And these 2's are canceled. And what do we get? We get x squared. See, and that was our original problem, huh? So it leads us back to our original problem. That's the idea of integration. We have the derivative. We're trying to figure out what was the original problem right here, which was x squared. So we add 1 to the power, and then whatever the power is, if it's a 2, we're going to divide by a 2. If it's a 3, we're going to divide by a 3. Whatever this power is, that's what we divide by. Strange, huh? Well, what if this problem was instead x squared plus 7? The derivative would still be 2x, right? But when we come back here, we can't find that 7. There's no way we can figure that 7 out. But we know there was some number that was maybe being added to this, so we put plus c. And c indicates that there was some constant, but we don't know what that constant number was. Maybe it was a 5, a 7. We don't know, so we just put c. Okay, so we're trying another little derivative here. Let's see if we can do it. An antiderivative. And they're going to look like this. They're going to be in this form. And they're going to have something in here. Let's make it x to the third. And it'll have a dx behind it. We'll explain a little bit more about the dx later, too. Okay, for right now, we just kind of call it dx. That's the derivative. This kind of turns into a 1 when you take the derivative, the antiderivative. So the antiderivative, we're going to take the x cubed, and instead of subtracting 1 like we're used to multiplying this by 3 and then subtracting 1, we're actually going to add 1 and put it over that power, 4 plus c. And now you just took the antiderivative. Weird, huh? Are you okay with that? Kind of follow it? Okay. So in the book, they have a problem like this. X to the 99 dx. See if you can figure out what the answer to this would be. That would be x to the 100 over 100. Pretty easy, huh? Plus c. This is like there's a joke. Where did that come from? Good. Okay, it's gone. Oh, you know what? Maybe I'm pressing on the, I don't know. Anyhow, there's a joke that these two calculus guys, professors, were working on this problem. They got a whole bunch of junk on the paper all over the place. And they finally, they've been working on this in this restaurant. And the girl would come around, the waitress would come around and ask them if they wanted some more coffee. And they're, don't bother us, we're solving this big problem, And they kept doing this, and she'd come around, like, you've been on this for an hour, would you like a refresher on your coffee? No, we're busy. Finally, they're shouting, yes, we got the answer. Maybe the answer was something like, x squared over 2, or say, or whatever it was. And they finally figured out the answer, and the waitress comes by, would you like some coffee now? And yeah, we're celebrating, And she said, well, you got it wrong. And they look at her and they said, what? We got it wrong. Yeah, she said, you forgot to add the constant. Okay, it was supposed to be a joke. Okay, they forgot to add the c. And so she was smarter than the two professors that were working this whole problem and knocking their brains out. Do you believe that? Yes, it's probably a true story.
Mr. Mitchell, I have a question.
Yes.
So how do you know when to add C? Do you just guess and
You always add C.
Always add C?
Always add C. We're going to do another type. This is called an indefinite integral. Okay, indefinite integral is what you're working on. Indefinite. So we always add C. That was a good question. Now, what we're going to do a little bit later in this hour, we do some definite ones. A definite one is going to look like the same thing we just did, except it's going to have a couple of numbers here. It'll have a beginning number, a large number, and then on the bottom I have a small number. And those we don't add to C because they have boundaries on them. We have definite boundaries on them that we go to. And I show you how to do those at the very end. And of course, this would be a dx. Okay. So these don't always have to be, this could be like a t in here, and then this would be dt. Okay. It doesn't always have to be an X. Usually it is, but you know, it could be a T or something like that. And it would be inside. Okay, so it's just really pretty easy. But sometimes they get a little complicated, like this next one, the square root of x dx. So in this case, it would be the integral of x to the half power, dx. Well, my hand isn't writing too good today. Okay. So then what we would do on this one is we have to add 1 to this. So that would be basically 2 2's. So this would be x to the 3/2 over 3/2. See, but that gets a little messy, plus c. So what we do in a case like this where there's a fraction, what I do, at least, is I just write the reciprocal. Like this is 3/2, I put the 2 here and the 3 up here. So if it comes out a fraction, I usually write it as 2 on the bottom and 3. So if it's written 2 over 3, we can take this 3 and put it on top like that and write it as 3x to the 3/2 over 2/3. So if you think, okay, we just kind of write the reciprocal. Well, actually, we're writing the same thing, 3/2, 3/2 like that. Let me make sure I gave you the right answer. Wait, did I do that right? Wait a minute, I'm wrong, This would be 3/2. So the 2 would go up here. Yeah, it has to be the reciprocal. I told you wrong. This would have to be 2/3, 3/2. 3/2 over 3/2. So we write the reciprocal here. Reciprocal of 3/2, 2/3. 2 on the top, 3 on the bottom. 3/2, 2/3. Did I confuse you? I confused myself, I think. Let me try another one like that. Let's say we had this one. The integral of the 4th root of x to the 3rd. So this would be the integration of x to the power over index dx. And that would equal, we're going to add 4/4 to that. So that would be x to the 7/4 over, and then we flip that over 4/7, like that. You could write, 7/4 and then bring the 4 up here, but it's kind of like just kind of a shortcut plus the c. Okay, here's another one. dx. Now the dx, sometimes is written between them, but you kind of assume that the dx is up on top, It would be a little harder if it was, okay. So this is, first thing we want to do is bring this up to the top. And we're going to add 1, right? So that'll give us x to the -1 over -1. Or we could pull that back down and say that's -1 times 1 over x. So that would finally end up to what? Maybe we could write the final answer as -1 over x dx. And not dx plus c. What am I saying? Plus c. Let's try the one in the book. Let's see if we can do that one. Am I okay to erase this?
Yeah, we're good.
You good? Okay. How about try this one, see if you can do this one. 1 over x cubed. It's kind of a different way because, excuse me, you already did, you know, your derivatives, and now this is just the reverse. So it's kind of hard. So this would be integration of x to the negative 3. So we want to, you know, pretty much like when we did derivatives, we kind of want to put it in this form. And it's like derivatives too. If you can simplify something inside here, you always try to simplify. So we're going to add 1. That would be x to the negative 2. And this would be over negative 2. Then we could plus c. And then we could bring this down. This would be 1 over negative 2. You could leave the negative on the bottom. We usually bring it up to the top, but you could leave it like this. It would be okay. You know, 1 over negative 2x squared and plus c. Write the answer that way. Or you can move the negative sign to the middle. Okay, so we did x cubed and we did x squared, but when you run into this problem right here, 1 over x dx, special case. This is always the natural log of x plus c. So 1 over x, we don't bring it up. We don't say x to the negative 1 and try to calculate it. It's just the natural log of x plus c. X cubed we bring up, x squared we bring up, but not 1 over x. So 1 over x cubed is not a natural log or anything like that. It's handled like we did up here. You know, you can see how we did it, this whole thing. But 1 over x, special case. Okay. Another special case, what is going on here, is e to the x. It's got a mind of its own or something. And that would be dx. That would be e to the x plus c. So these two are kind of special cases, 1 over x and e to the x. We use those quite often. Okay, so you're saying, okay, yeah, that's great. Well, what if I had the integral of e to the 4x? What if I had something like that? So sometimes this one's a little bit harder. This would be not really super hard. It's e to the 4x, doesn't change, over 4 plus c. So we kind of put it over the 4 there, and that would be the result. So when we have something with a kind of a fancier exponent on e to the x, it's e to the 4x over 4. And that way you don't have to do a whole bunch of work. The other thing we have to remember is sometimes when you have a number, like maybe you have 3x to the 5th, dx, that we can take that number out. And sometimes it's helpful to do that. If you pull that number out of there, then you don't have to worry about it. My pen's messing up. This would be x to the 6 over 6 plus c. And then you can kind of reduce it. X to the 6 over 2. So now you know integration, at least the easy integration. So what are you thinking? You're thinking, give me a harder one. Okay, yeah, I know you were thinking that. Okay, so if you have your book on 393, they have a problem like this. If you don't have your book, that's fine. I'll write it down anyhow. Okay, so we have a problem like that, right? Good. Okay, so notice the dx, we can write this as 3 separate ones if we wanted to. We usually, after you get faster, you probably wouldn't want to put this step in, but, starting out, you could write this as 3x squared dx plus the integral of 7, oh, this should be an x. I think this was an x to the 5th, I'm sorry. 5. Plus the integral of 7x squared. If these were both squares, you would have added them. Dx plus the integral of 8. Okay, so this one we could pull out the 3, or you can leave it if you want. And 3 is just going to stay. This would be x to the 6 over 6 plus this would be 7 x to the 3rd over 3. See? It's pretty easy to do them. You're just adding 1 and putting it over whatever that thing is. But here, this is going to be 8, but we're going to add an x. You know how we usually said that was 0 when we were doing derivatives? Now it's going to be 8x. It's going to get bigger. See, all these terms are getting bigger. So it's 8x. The powers are increasing. So instead of just being 8, this should have a dx behind it. So that dx kind of turns to an x, kind of like, maybe you can think of it that way. It gives you an extra x that you add to this. And that's where you get the 6, you get the 3. It's not quite the same, but plus c, you might have some constant there, we don't know. And of course, then you might simplify this part to 1/2, And then you got your problem, huh? So we can do multiple things. If you want to write this step down, you can, or some people just go from here to here, 3x over 6, here to here, here to here, and not have to write so much. Okay, let's see what we got. Any fancy dancy things in this section. Okay, let me grab a couple of problems out of the thing. So let's try this one. What would that be equal to?
Wouldn't it be 4x?
Yes, very good. And if you forget the C, I'm not going to count off for it, but, you should kind of put it in there. You usually do. All right, let me give you another one. Usually they put the whole thing in the parentheses, they put the dx there and then the integration sign symbol. So this would be, you could break them down into separate ones, or maybe you can just do it a little faster. X cubed over 3 minus x squared over 2. And this is the one that usually throws a lot of students, and I want to put a 0 because you're used to doing it that way, but this becomes 2x plus c. So add, put it over, add, put it over, add an x. Okay. Let's see if we can do this one. Okay, so that 5 is going to stay. And this is going to be e to the 3x over 3. that. Let's see. And if you want to put the line under the whole thing, then it's fine. You can do it like that. Or you could write it like this. You know, sometimes they write it this way. They both mean the same thing. Chris, what are you doing? I see you. Okay, so let's go to another little thing. So what are we using? Oh, why don't we give you a super hard one? You ready for a super hard one? Okay, let's try this one. This is number 46 if you're using the book. If you can do this one, you get the whole thing down pat. And technically, these are like a little fancier than I've been making them. This is a tough one. So we're trying to simplify it a little bit, maybe before we go ahead and take it or whatever. This would be 1/5 x, so let's bring this up to the top. It would be a negative 1/5. Power over index 1/5. I just write it here. And because it was on the bottom, I had to bring it up to the top, right? Plus 3 over 4 e to the 6x. I don't think we can do anything to that. Minus 7. But we want to be careful on this one. You don't want to bring that x up because this is 7 times 1 over x, which is ln x, see? And of course, this would be all dx. So let's go ahead and take each one. So this would be 4. See, we want to add 5/5 to it. So that would be 4/5. And then I usually write the reciprocal of that. Instead of 4/5, it'd be 5/4. 4/5, 5/4. I just leave that one. Plus, this would be 3, 4 e to the 6x over 6 minus 7 ln x plus c. So this is kind of tricky because see how we brought this one up, but this one we're not going to do it because if it was an x squared, I would bring it up. But if it's just an x, then that becomes 1 over x, which is ln x. Okay, so then this would give me these 4s looks like they're going to cancel. This would be 5 to the 5x to the 4/5 plus 3 can go into 6 2 times. So this would be e to the 6x over 8 minus 7 ln x plus c. So in your book, there's some kinds you can practice on this and stuff. That's the correct answer. Pretty cool, huh? So you're learning quite a bit today, moving this up. We're going to look at one other thing. So,
Hey Chris,
So
are you going to put this on YouTube?
Chris, you're muted.
Okay, what's your, like, where do I search to find it? Like, what is, yeah. Okay, thank you.
Good, that would be good, because then you can kind of review, because we've gone through this pretty fast, and it is confusing, especially the ones with the fractions. Huh? These get kind of confusing. So that's good. You know, you have to reduce the fractions, and especially, you know, special cases like x and e to the 6x. Those are special cases. So you want to be kind of careful. It's not too hard, you know, but it's something you don't do every day. So the other thing I want to go over is, where do we use this? Okay, we saw that we used derivatives on related rates, but on antiderivatives, one use of them, there's several uses, but one we're going to kind of explore is trying to find the area under an object. Okay, so say we had a curve of some sort, and it's going, and we have boundaries on this curve, maybe from 0 to 2. And we want to find what is the area inside here. So if we know this equation, if we know this equation right here, this, whatever the function of x is, maybe it's x cubed plus 7 or something, we know that formula, then we can find the area inside here, you know, as long as we have this formula. So that's what we're going to do right now. This would be, let's look at your first worksheet before I jump over to that one. Let's look at your very first worksheet and see if we can do a problem off of it. Look at problem, I'm going to jump to problem number 10, actually. I'm sure you won't have too much trouble with the real easy ones, but on this one, you know, it's kind of a little strange. So what you want to do on a problem like number 10, do you see that problem on your worksheet, 4.1? This 10 is just here. Okay, what you want to do is simplify these, put each one over x. Like that, so that you have it a little bit easier to work with. Right now, I wouldn't be too concerned about the dx. We're going to use that later on for some stuff. So this is really 4 times 1 over x. And this is really, the x's are going to cancel, right? So this is really plus 3. And here the x's are going to cancel a little bit too. X squared. So this is 2x squared dx. So finally, our answer would be 4. You know, so sometimes you want to do a little, you know, simplifying before you jump right into the problem. You know, rewrite it as each one over x, and then simplify, and then go ahead and take your thing. This 4 is going to stay, but 1 over x is ln x. Plus 3 doesn't disappear. It's 3x plus 2. And this becomes, we add 1, and we put it over whatever that new power is, and we put it over 3 plus c. So they really change forms, huh? It doesn't look anything like the original problem. Well, maybe somewhat, but not a whole lot. So it's kind of weird, huh? So this becomes Each one was over an x, and this became 3x because the x is in cancel. Do you follow that? So, you know, work on these a little bit and you'll be okay on them. It might not be too bad. So number 5, if you look on your on that sheet, number 5 is going to be an ln(x) problem. Natural log of x. It's not going to be, you're not going to bring that x up to the top. You only bring it up if this was an x squared, then I would bring it up and write it as x to the -2. But if it's just an x, 4 over x, it means 4 over 1 over x. If I have the integral of 4 over x squared, then yes, I do bring that up. And I add 1. That would give me 4x to the -1 over -1, or -4 over x. You know, so that would be quite a different problem right there. All right, I'm going to look at sheet number 2 and show you how to do these. Okay to erase this? Okay. I'm going to erase it. Okay, on sheet number 2, you're looking at problem number 1 here. They got a drawing here. It's a parabola. And one way we can figure out what's the area under the parabola is to count up all the little boxes. And this would give us an approximate idea of the area under the curve. So you wanted to go from, and they got like, the equation of the curve was this. And they wanted to go from -5 way over here at -5 all the way over here to +3. And one way we could do it is just kind of approximate it by counting little squares underneath these things. This is what we call Simpson's law or something like that, where we just count boxes. But you'll find out it's not very accurate, you know, but it gives you a kind of an approximation. I think if you added the boxes here, it'd be like, the area would be like 25 or something like that underneath here. And you find out it's actually around 33, so it's not really totally accurate. But it's one way to do it. So another way we could do this, instead of doing all that, and I don't want to get on this problem because this one's a little bit harder. Let's try one of the easier ones. They want to find the area under the curve of 2 dx. Well, let's see what that curve would look like. You would have just had a straight line at 2 kind of coming across here, and they wanted it from 5 to 0, so 0 to 5, and we would kind of figure out that it's just a straight line, 2, and it would be the area inside here, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It should come out to be 10. The area under that curve would be 10. It would be 10 squares underneath this thing. So let's see if we come up with the same answer. Okay, so this is what we call a definite integral. 5 to 0, 2x, 2 dx. So what's the integration of 2 dx? That would be 2x, right? I might have drawn this wrong, I don't know. And then this is going to be from 5 to 0. So we write it like that. Put the big number on the top. Then what we're going to do is we're going to calculate, we're going to put the 5 in here. We're going to substitute a 5 for x. And then we're going to always put a minus, subtract, and then we're going to put a 0 in here. In this case was a 0, whatever number it is, you know, this happened to be a 0. And we're going to calculate, and that would be 10 minus 0 is 10. You notice we don't put the plus c. So the area under this curve should be 10, and that's what we kind of calculated out, that it would be 10 underneath there from 0 to 5. It's just a straight line shooting across, and so it would be 10 was the area from 0 to 5. There would be 10 units, or it would be basically the width was 5 and the height was 2, so area is 1 times height. 2 times 5 is 10. 10. Okay. So let's try this next one. Let's try number 6. Here we have one that's 4 to -1. And it's going to be 4dx. So we're going to take the integration of that, which would be simply just 4x. These are pretty simple integrations. And it's going to be from 4 to -1. Different books have different ways of marking them. I mark them this way. Different people do it a little different way. You know, I just draw a line down, and the top is where I'm going to start, and the bottom is where I'm going to end up. So I put a 4 in here. This is going to be 4 times 4. I'm replacing this x with a 4. Minus, and then it's going to be 4 times, instead of x, it's going to be -1. And then I'm just going to calculate 16 minus, well, a negative times a negative is a positive. So that'd be plus 4. And that comes out to be 20. So the area under that curve would be 20 units, whatever they are. And we can find the area without even drawing the curve itself. It would be 20 units. Well, you're saying, okay, what if it was like number 10, where they have actually, well, let's try number 9. Here we have an actual little tougher problem. The integral of 5 to 2, and our equation was 10 minus 2x dx. Should have been a parentheses there. Equals. Okay, so let's do the integration of this thing. What would that be? 10x minus 2x squared over, and we want to be kind of careful on this one because it's easy to forget, over 2. X squared over 2, see? So these cancel. So it's really 10x minus x squared from 5 to 2. Okay, so when you take the integration of that, the 2 stays. This becomes an x squared, but we got to put it over. This became an x to the 1, but if we put it over 1, it's not really going to change anything. So that's why we don't, you know, you could write it as 1 over 1. But we usually don't. Okay, we're not done. Now we got to put the 5 into both of these parts. So this is 10 times 5 minus 5 squared. Okay, that's replacing all these x's with 5s. Now we're going to subtract, and we're running out of time here, so I can't spend too much time. And we're going to put a 2 in here. 10 times 2 minus 2 squared. There you go. I guess we didn't need a parentheses here per se. All right, so what do we got? We got 50 minus 25 minus, I'm going to distribute here 20 plus 4. Distributing those signs and calculating all this out, and it should be 54 minus 45. Let me write it. I'm frozen up again. So the area underneath this curve from 5 to 2 is 9 units. If I calculated it correctly. Okay, so I'll let you work on those two. The very 1 and 2, you're just taking a guess at what the area is. You can actually try to do it with a derivative, antiderivative, and see if you can actually come up with the exact answer. If not, it's just taking a guess at what the area is underneath. And this is an exact way of finding the area underneath by using the antiderivatives. Okay? Then we're getting some tougher stuff next time. I'm going to sign you off. Do you have any questions? Anybody have questions?
We're good, Mr. Mitchell.
And Chris said he recorded it for YouTube, so you can get it there. Okay, I'm going to end the meeting. Yeah. All right. Thank you, Chris. We'll see you guys.
Thank you, Mr. Mitchell. Bye-bye.
Thanks, Mr. Mitchell.
Bye.